variable x is the thing we follow through. X represents the number of successes you basically have. Like if I'm looking at the probability of rain for 4 days, my X value will go from 0 to 4, because I could have no days, 1 day, 2 days, 3 days, 4 days. So your random variable is the one that's associated with your outcomes. How many outcomes will you get? What will they be? 9 out of 10 times you get the 0. There'll be once or twice where they may label, like we do one with the hurricanes. The hurricanes are labeled 1 through 5 because there couldn't be a 0 hurricane, right? It would not be a hurricane. So those are the times you might not see a 0 in there. But most of the times you will say, I can have none of these, like successes versus failures. Before we even get to your binomial distributions, we're going to talk about a probability distribution first. Now, your X variable can be one of two types. It can be a discrete value, or it can be a continuous value. And you should have this on your note page as well. Now, continuous means continuing. So if I drew a graph, a continual line goes like this, continuous. A discrete graph has a finite or countable. It just has these little dots, these little points. They don't connect. So a discrete graph, think of it this way, are whole numbers. They're integers. A continuous counts all the little pieces in between. They can be fractions or decimals. For instance, discrete. The number of books on TJ's desk. He can count the number. Can he have 2.5 books? No. He can have 1 book, 2 books, no, none, 5, 10. Discrete. The number of pencils in your pencil case. Discrete. You might have a small pencil, but it's still a pencil, right? So you're discrete. It's countable. The number of ounces of coffee in Danielle's mug here. Discrete. Does it have to be 1 ounce, 2 ounces, or 3 ounces? No. She could have 2.5 ounces. So if anything has a fraction, a decimal, it's continuous. If it's a whole number, it's discrete. This is very important that you understand this, because when we look at your graph and we looked at your discrete numbers, remember when we made those boundaries? Remember when we made the boundaries for your bars? Because your numbers were discrete. So we said, well, the bars would have gaps in them. If it went from a 1 to a 2, it would have a gap. So we did the little boundary, the plus or minus the 0.5. We connected them. That is a discrete that we had to make into a continuous measurement. So these are the things we're going to look at for this. It's not really that bad. Most of it is kind of common sense. So for instance, you're going to decide whether your variable is discrete or continuous. So number 1 says, let X represent the number of Fortune 500 companies that lost money in the previous year. First of all, what are we looking at? What does X represent in a short sentence? The number of, right? The number of these companies. How many companies? So how many companies? Is this discrete or continuous? Discrete. They're countable. 1, 2, 3. I can't have 3.5 companies. This is discrete. Let X represent the volume of gasoline in a 21-gallon tank. We want to look at the volume. Is volume discrete or continuous? Continuous. My science people shaking their heads. Continuous. Okay, I can have with a decimal, with a fraction. It doesn't have to be a whole number. All right, so take a look at, try it once. Let X represent the speed of a rocket. What would you say? Continuous. You say to yourself, can it go 400.2 miles per hour? Yes. If it only could go 5 miles per hour, 6 miles per hour, 7 miles, and never have a decimal, then it's discrete. Let X represent the number of calves born on a farm in 1 year. Discrete. These are countable. Okay? Easy, right? It kind of makes sense. You ask yourself, if you can make a fraction or a decimal, it's continuous. That's what you want to ask yourself. when we talk about your discrete probability distribution, we need two factors to happen. And I put this on your notes as well. For it to be a probability distribution, in other words, I'm going to put all my x's here, my x's from 0, 1, 2, 3, and I'm going to make a probability out of this. I'm going to take its frequency, I'm going to take its total, I'm going to make a probability out of this. For it to be a probability distribution, there are two things that have to happen. First of all, just basic. You know your probabilities are between 0 and 1, inclusive. 0 meaning impossible to happen, 1 meaning certain to happen. If it's 0, you only get one probability. If it's 1, you only get one entry in your table. It's 1. The other criteria is that the sum of all your probabilities equal 1. And we know this. If we roll a die, and the die has 1 through 6, the probability of 1, 1, 6. The probability of 2, 1, 6. All of them have a probability of 1, 6. What is the total if I add them all up? 1. All your probabilities, all the possible outcomes in a probability distribution have to total 1, which makes perfectly good sense. So our probabilities, and we know, have to be between 0 and 1, and the sum has to total 1. And we've used this concept before. We've used both of these before. So we're going to apply that to making this table. All right. So we're going to construct a probability distribution. And I'm on page 192. I think I put this in your notes too, right? Constructing your distribution. I tried to give you like the basic part so that you can expand on those. Basically, you make a frequency distribution. Isn't like your relative frequency part over whole? So you're making a frequency distribution. You're finding the sum of all your frequencies. You're taking each one, dividing it. That's your relative frequency. And we're checking the two things. These are the two things that make it a probability distribution. That the sum of all the parts add up to 1, and that each probability comes between 0 and 1. Good? Okay, now I'm going to jump over this first. And I'm going to go over to example 3 and 4 first. Because I want to verify that they're probability distributions first. We're going to verify that this is actually happening before we figure out how to do this. So I'm jumping to example 3. We're going to come back to 2. Now, here's an example of a probability distribution. It has the random variable x. This is your random variable. And the days of rain can happen 0, 1, 2, 3. I could have 0 days, 1 day, 2 days, 3 days. Is this value continuous or discrete? Discrete. Okay, I'm just counting the days that it rained. So they come up with this probability distribution, and they say, verify that this is a probability distribution. We check two things. One, that each probability is between 0 and 1 inclusive. And 2, what's the other one? Good. That the sum is equal to 1. So the first thing we look at are your probabilities. Are they all good, valid probabilities between 0 and 1? Okay, so that part's good. Then we say, does this add up to 1? And we add them all up. You can do them in your calculator. Yep. So therefore, yes, this is a probability distribution. I just want you to verify these first. Okay? Now, jump to example 4. Here's 2 other examples of probability distribution. Because probabilities can be fractions, right? So, the first one. We look at all the individual probabilities. Does it meet the first criteria between 0 and 1? Yes. So the first one is good. Then we say, do they add up to 1?
No.
No. What do they add up to? 1.07? So they do not add up to 1. So therefore, this is not a probability distribution. Okay? Take a look at the second one. It's not. What?
-20 and 5/4.
Ah, good. God bless you. They got -1 and a 5/4. First of all, 5/4 is greater than 1, isn't it? That can't happen. It has to be between 0 and 1. And do we ever have negative probabilities? No. No. We may lose things, but we don't have negative probabilities. Okay, so this guy was not a probability. God bless you. Okay. All right. I want something all sticky here. All right, take a minute and look at these two. So Aaron, what do you say about the first one? Oh, you did the last one? You like the decimals better than the fractions? How do you add up all those fractions? Do them in your calculator. Or you can find a common denominator. The best way to do it is to find a common denominator. What is the common denominator? 16. So very good. So 8 goes into 16 how many times? There's a 10. 4 goes into 16? 4. Add your numerators. 1 plus 10, 11, plus 4, 15, plus 1, 16. That one's good. Put them in your calculator. If you're going to do them in your calculator without your fraction key, make sure you put them in parentheses like this. Just make sure they're in parentheses. So it does and actually it should do it anyway without the parentheses. It'll do the divide then the add. Alright, so we agree this is a probability distribution. Yes. Second one. Do they fall between 0 and 1? Yeah, that one's good. What's their sum? 1.04. Not a probability distribution. So, two things to be a probability distribution. The probabilities have to be between 0 and 1, and the sum has to equal 1. Those things we've been using. Whenever we make our trees, your probabilities are between 0 and 1, and all your probabilities add up to 1. All we're doing now is taking this, putting this on the table. Alright, so let's jump back to making a probability distribution. I would have done it in a different order, but I decided not to. Okay. We're going to make a probability distribution out of this. They give you this chart on the left-hand side. I'm on page 192. An industrial psychologist administered a personality test of passive-aggressive traits to 150 employees. Individuals were rated on a score from 1 to 5. See the 1 to 5 in our table? That's one of the cases we don't use a 0. You can't get a 0 on this test. 1 being extremely passive, to 2, down to 2, all the way to 5 being extremely aggressive. Okay. A score of 3 indicates neither trait. Neither trait. You're kind of in the middle. You balance out your aggressiveness and your passiveness. Okay? These results are shown in this table. What should this frequency add up to? 150. Good, because we surveyed 150 employees. We wanted to see, are they passive, are they aggressive, and where do they fall on our scale? Okay? Now, we're going to take this and we're going to make a probability distribution for this random variable x. And then we're going to make a graph. It's just a relative frequency graph. All we're finding is your relative frequency. That's your probability. So we're going to take this and put this in a table. So since this is 150, I made this way. I could have put this over here. We could do it over here as well. You're going to say 24 over 150. 33, this is your relative frequency. Part over whole, this is your probability. Part over whole. And rule of thumb, 3 decimals. Now, they went to 2 because it's probably terminating because it's over 150. And do you see how they worked it out? 24 over 150. 33 over 150. So they got their probability distribution. Now, if you do out these numbers, they better come between 0 and 1, and they better add up to the total, because you made it that way. You figured out your total ahead of time. So, yes, they're all between 0 and 1, and these have to add up to 1. Now, sometimes when we round, like on 3 decimal, you may be off slightly because of the way the rounding goes. And then just make a little adjustment to make it equal to 1. Like sometimes when you round up too many times or down too many times, it will have like a .001 effect on it if you're going 3 decimals. But just make that adjustment. So this is the column we're looking for. Part over whole. Relative frequency. This part is the part we're graphing. This is your relative frequency graph. So when you do your relative frequency graph, I should have moved it up first. Let's make a graph out of this. This is no different than your other graphs.
So once you find the probability, you can just plug it right into the graphs?
Yeah? You just make a relative frequency. God bless you. Now, same thing we did before. We're going to make a bar graph. We're going to put a title, passive-aggressive traits. Okay? This is your x-axis. This is your x. They're discrete. This is my x, my trait. This is your probability. Before we put relative frequency, it's your probability. It's the same exact. Your relative frequency, we did the y-axis with decimals. We do the same thing. Consider your decimals like money. It's the easiest way to set your axis up. So I want to go from 14 cents, go from the 0, as high as 30 cents. So if I go by 0, 0.05, 5 cents, 10 cents, 15, 20 cents, 25, 30 cents.
What if it doesn't add up to 1? Do you still have to do the graph?
It has to add up to 1.
Or if it doesn't,
The problem is it may not add up to 1 because of the rounding, but because you do part over whole, and those are all the parts that added up to the whole, your probability will add up to 1. The only time it may not is if you rounded, and like I said before, if too many of them rounded one way, you might be like a 0.01 off, a 0.001 off, and then just make a little adjustment to one of them. And being that is not going to be too bad. So, I do my bars. At 1, I'm 0.16. Remember doing this? At 2, I'm 0.22. At 3, I'm 0.28. They have to touch. Now, they're okay touching because we use this as a midpoint of our bar. So if we didn't and we went from 1 to 2, we would be in trouble. No, we would be in trouble. These are like our midpoints of our bars. 20, under this, and 5.14. Okay? It's almost fairly symmetrical, isn't it? So what would you say the mean is of this graph by looking at it? Mean, middle, mode, median? 3. So what does that mean? That in terms of their traits. Most people are neutral. On the average, the traits for this 150 employees was neutral, was neither passive nor aggressive. It's very, very close to being symmetrical. And when it's symmetrical, your mean, medians, and modes fall smack in the middle. And there's your mean right there. So your mean would be 3, meaning they kind of averaged out. Okay, does this make sense? Yes? All right, you're going to try at your desks. You're going to try this next one. Oh, come on. Losing my voice. So your graph, make sure you give it a title. Guys, don't pack it up. I want to finish this. These are your sales for your new employees. All the X's go down here. Make sure you start at the 0. Now, be careful of this. Your 0 technically starts here, but your X needs to make a bar. So on the bottom, we're going to start your 0, excuse me, a little bit in further here. 0, 1, 2, 3, 4, 5, 6, 7. Put your 0 there. Normally your 0 is in the corner, but 0 is an X value in this. And then go from here. 0, 0 to your highest number. What, 20 cents, right? So go by 0.05. Spread them out a little bit. And then make your bars. Okay? Label. These are your sales per day. Taken right off your graph. This is your X value. This is your P of X. Just leave this P of X. Can everybody do this part? All right, so at the 0, we're 0.16. At the 1, we're 0.19. Then 0.15, 0.21, oops, a little higher. 0.25, 0.09, 0.1, 0.08, and a little guy over here. So you can kind of see where your distribution is a little bit better. Where is it skewed? To which side? To the right, it did. It follows the tail. So our skew rules work the same. And tomorrow we're going to see what the skew means for your probability.